In this video, we're going to investigate how to characterize and analyze DC circuits for which we cannot reduce everything to an equivalent resistance. That's what we've been doing so far. We've been showing circuits. I take the resistors that are in the circuit, I reduce it down to some equivalent resistance, and I solve using Ohm's law and the power equation and things like that. Well, in this circuit, I have two EMFs. Now, that's not necessarily a deal breaker, but in this arrangement, it's a deal breaker. It's not obvious to me at all how to reduce R1, R2, and R3 to some sort of equivalent resistance. If E2 wasn't there, it wouldn't be a big deal, right? R1 and R2 would be in parallel. That would then be in series with R3, and I could handle it. But the presence of this EMF has thrown me off my game. Again, the fact that there are two EMFs doesn't always mean I can't work this way, or I can't work that way, but in this arrangement, I can't. So what are my options? I need to come up with a set of equations that I can solve. That's all we ever do in physics. We come up with a set of equations to describe a physical system that I can then solve to determine particular characteristics. So in this one, we're going to look at how to proceed. To do that, let me introduce you to Kirchhoff's laws. We'll say Kirchhoff's rules. I like laws. We'll go with that. There are a couple of them. Actually, exactly a couple. There are two of them. The first one is called the junction rule, which I think is the easiest to see. The idea with the junction rule is that, I'll write it down here. The junction rule says that at any junction, the current flowing into that junction has to equal the current flowing out of that junction. I hope that makes some sense. We're not allowing the current to go anywhere. That is to say, to disappear. There are no sources or sinks at a junction. Now, you might be argued that there's a source of a current here, maybe even a sink, depending on how you look at it. But at a junction, we're not putting any EMFs at a junction here. So what do I mean by junction? It means where these wires split. We've talked about this in terms of the current flowing here. It's going to split. Part of it will go through R2, part of it will go through R1. We talked about it in the terms of charge when we were talking about capacitors. So there's a junction here, and there's a junction here. So at each of these junctions, I have current flowing in and I have current flowing out. And I should point out at this point, I actually don't know what direction the current's going to flow. It would depend on magnitudes of EMF. It would depend upon the relation or the arrangement of the resistors. I just don't know how current is going to flow. So what am I going to do? The answer is I'm going to take a wild guess. Not a wild guess. I'm going to take a guess and not care if I'm wrong or not, which seems kind of strange. But as it turns out, I'm going to guess at the current direction. And if I'm wrong, that will show up later in the mathematics as the presence of a negative sign, which will then tell me that, okay, I picked the wrong direction. But in general, that's not that big a deal. So if I look at this, I'm going to assume that current is coming out of E1 like this. And because this is the first current I've labeled, or the first one I've drawn, I'm going to label that I1. Now, what I'm saying is anywhere along this leg of the circuit, all through R3, E1, and up here, specifically these two components, R3 and E1, everywhere along that leg, I1 is flowing. And so I normally wouldn't draw this, but because it makes it convoluted, but just to show you what I'm talking about, this is also I1. And that should make sense. Because if I'm just looking at this lower portion, that is, I'm not encountering the junctions yet, I've got a series here. R3 and E1 are in series, if you want to think about it like that. And so the current doesn't have anywhere to split. The same current has to be flowing here than that is flowing here. And I've been consistent with my directions. Again, I just guessed at the direction. I don't know if current's flowing this way or not, but I'm going to guess that it is. At this junction, though, something happens. The current will split. Part of it will continue up, like that. Part of it will go, I'll draw it down here, to the right like this. Again, I actually don't know if those are the directions of the currents in those legs, right? I've got this leg, I've got this leg, I've got this leg on top. I don't know if I'm right or not. I just don't care. It's gonna work out in the end. I will be able to tell if I'm right or not, and then fix my wrong guess. I could be right, it could be wrong. But at any rate, these two currents are no longer I1. Right? We know that the current's gonna split at the junction. So let's label this one let's label this one I2. And I've drawn this a little too small. And this will be I3. Okay, fair enough. Well, I3 then is coming over here and down. Everything in this leg is I3. Again, I normally wouldn't draw all of these currents in there, but I think it helps us to see what's going on. So in my guess, I1 is coming out of E1, going up to this junction, splitting into I2, which is flowing through R2 in that direction. I3, which is flowing through R1 in the upwards direction. And then notice I3 comes around, I2 comes around, I3 and I2 come back together at this junction. And then flowing out of that junction is I1. That should make some sense. If you're thinking of this like a river, which is always helpful to do, I think, it's like the river comes up to an island, and part of the river goes this way around the island, part of the river goes the other way around the island. Fair enough. After the island, those two parts of the river come back together and reform the river. And so that's the essence of the junction rule. The junction rule says the current flowing into any junction has to be the current flowing out of that junction. So if I just look at this junction, what is flowing in? I1. And that's all that's flowing in, but I do have two things that are flowing out. So what I can say is IN, which in this case is I1, is equal to I out, which as I've drawn it is I2 plus I3. And there is one equation that I can use to solve this system. I've derived a relationship between the currents flowing there. You might say, well, what happens at the other junction? Fair enough. In this case, if I look at the current flowing into this junction, I've got I2 plus I3. That's got to equal the current flowing out of this junction, which is I1. And there's nothing wrong with that equation, but it's redundant. It's the exact same equation I got over here. I can't use more than one of these to solve my system because it's the same equation, right? I've only gotten one equation. Now, that's because this is a relatively simple circuit. If I had different junctions with different currents flowing into and out of them, like if I had an I4 and an I5 and they were involved in another junction, then there absolutely would be another equation I could get out of that. But in this simple case, I can only get one equation there. So that's the junction rule. Generates one equation, or at least generates some equations, in this case just one. Two, though, is called usually called the potential rule or the voltage rule. I'll call it the V drop rule. We know what a voltage drop is, right? As I move across a resistor, I experience a change in electric potential from one side of the resistor to the other. That is, if I measure across the resistor, if I drop two probes of my multimeter, my voltmeter here, I will measure a change in potential across that resistor. This says basically the sum of the voltage drops around any closed loop. Closed loop might be a little bit redundant, but that's okay, is equal to 0. Okay? And you might go, wait a second, if I'm going to sum up voltage drops, if I'm going to sum up anything, if I'm going to add a bunch of stuff together and get 0, then either all of that stuff is 0 or I've got some positive and negative values in there. That's the only way I can do that. And we've already seen that voltage drops are not going to be 0 across the resistor. So we're going to need to look at some sign conventions to handle this. So let me take this paper away. I'll come back to it in just a moment. And let me talk about sign conventions for voltage drops. So let's get a resistor like such. We'll call this R. And we'll say that there is a, well, I'll do two different currents. We'll say that there's a current, there might be a current flowing this way. We'll call this I right. And there could be a current flowing this way. Now, of course, not at the same time. That doesn't make any sense. What I'm saying, this will be I left. What I'm saying is, in general, if I'm looking at how at some resistor, I might see a current flowing to the right. In another case, I might see a current flowing to the left. So these won't happen at the same time. That's not what I'm saying. But if I'm analyzing how the voltage drops, to this point, we've always analyzed voltage drops going in the direction of the current. So let's start there. We know that V is equal to IR. And furthermore, we know, this is how I calculate the magnitude of the voltage drop. We haven't worried yet about the sign. And so here's my convention. If I am following the current in its direction and I go across a resistor, crossing R in, make sure I'm still in frame, in the direction of the current gives V drop negative. Crossing R in the direction of the current gives me a negative voltage drop. That makes some sense to me because I've been encouraging you to think about this as this current flowing in some direction, like water flowing downhill, right? Which is why rivers flow in the first place, because they're going downhill. So if I'm going from uphill to downhill, I'm getting a negative change in potential. That makes some sense. If I'm going the other way, right? If I'm analyzing this system to the right here, if I'm following some loop around and I find that I'm working against the current, it's like I'm climbing back uphill. So let me say, and that would be a positive change in potential. So let me say crossing R oppositely to the direction of the current gives V drop positive, right? So this will make more sense when I show you how we're going to analyze in just a second. But if I'm analyzing some voltage drop and I'm moving in this direction, I'm analyzing to the right. In this case, I'm going with the current. So I find that my V drop is negative. If I'm analyzing to the right, but the current's moving this way, if I'm working against the current, I'm going to find that my V drop is positive. I'm climbing uphill. So those are the sign conventions for a resistor. Now I also have sign conventions for an EMF. What is an EMF? Well, that in effect sets the height of my hill and the bottom. It sets the height of my hill, right? If I'm going to hold the negative terminal at 0 volts, or I'm going to set my 0 point at the negative terminal, then the positive terminal is at some positive potential that determines the quote-unquote height of my hill. So here's how I will say that. If I have enough room to do this. So remember, these symbols mean positive and negative. If I look at this, if I'm analyzing this system, I'm moving around a loop, and I move in this direction. So this is not my current now, this is my analysis. If I'm moving from negative to positive, in effect, the battery is pumping the current back uphill so it can start its downward trek again. This will be a V drop positive. I'm going uphill. Now, if I cross the current, I'll do this in red, and not cross the current. If I'm analyzing and I cross the EMF from positive to negative, I get a V drop negative. And in effect, I'm jumping off a cliff. So I'm increasing in potential as I move from negative to positive. I am decreasing in potential as I move from positive to negative. So it all depends on how I choose to analyze this circuit. So those are my sign conventions. Hang on to that, pause, write down whatever you need to see on this video. Make sure you can see everything. Now, let's go back to this and try to figure out what the heck I'm talking about. So what I can do with this circuit is redraw it first of all, because it's really small, which I'm going to do in just a second. But what I can do now is I can determine some loops to analyze. Why do I need to determine a loop? Because I've got to satisfy this rule. If I'm going to come up with an equation to describe the system, I need to find some closed loops. I see 3 possible closed loops in this system. Here, the one at the bottom is one closed loop. The one on the top is a closed loop. I could also form a closed loop by going around the outside. So there's 3 possible closed loops I can come up with here, right? One here, one here, one here. Okay. Maybe you can take a second to convince yourself of that, and then let's redraw this circuit a little bit bigger so that we can see what I'm doing. Okay. All right. Here will be my circuit. And here's R1, R2, R3, E1, and E2. All right, so now my task is to determine the loops that I'm going to use. Oh, well, let me put in the currents that I've drawn. So I'm only going to draw in one here. I've guessed that this is I1. I've guessed, what did I call this, I2. And I've guessed that here is I3. That's all I'm going to draw. You have to recognize that I1 is flowing over here too. I3 is flowing over here also. But I'm only going to draw it like this because it's going to get convoluted really quickly. So now I'm going to determine some analysis loops, how I'm going to analyze this circuit. And so I need to determine the loops that I'm going to use and the direction in which I'm going to analyze. That is your choice. It is arbitrary. It's not going to affect your outcome. So let me do this. Let me, just for the sake of, this is not what I would normally do, try to change things up. Let me draw this loop. So this is my analysis loop. I'm going to analyze this circuit, analyze this loop of the circuit by starting here, moving around through this resistor, and then back here. I'm going to have to end up where I started, so maybe it'd be better to draw to close it off. But I'm going to have to end up where I started. Now, I could do this loop as well, but I think what I'm going to do is this loop. So I'm going to come around the entire outside of the circuit. And that's terrible, but it's okay. And I'm going to analyze in that direction. So just to remind myself of my direction, let me go ahead and put that in. You don't have to do that. This is just to remind me of what I'm doing. Okay, so we'll call this inner one. Let's say this is loop 1. I'll say this is loop 2. Okay, so I need some equations I can solve to determine the system for any number of unknowns. I don't know the EMFs, I could not know the currents, I could not know some of the resistors. In general, I'm going to have to come up with as many equations as I have unknowns. In this system, you'll see I can only come up with 3 equations, so it would be 3 unknowns, and we'll talk about why that is. But we know already the junction equation because I looked at it at the previous page, but let's remind ourselves. If I'm looking at this junction, I've got I in equals I out. Flowing into that junction, I've got I1. Flowing out, I've got I2 plus I3. And there is one equation that I will be able to use to solve this system. I need a couple more. So now I turn to my loop rule. My loop rule says that some of the voltage drops around every closed loop will end up being 0. So I've got 2 loops. I'm going to get 2 equations out of this. Let's do, I'll circle this 1 to remind you that it's for loop 1. Loop 1, I said I'm going to start here. It doesn't matter where you start as long as you finish where you started. So let me start here on the positive terminal, and I'm going to move around. Notice if I3 is flowing as I've indicated it, as I'm analyzing in this portion, I'm actually working against the current. I'm not really working, but I'm analyzing in a direction opposite to the current. Current's flowing up, I'm going down. So I've got to keep that in mind. The first component I come to is R1. There's going to be a voltage drop across R1. So what is that going to be? Well, we've seen from Ohm's law that the voltage drop across R1 is going to be I3 R1. Just IR, but I subscripted what they are. Now I have to worry about the sign, and remember my rule. If I'm analyzing in the same direction as the current, I get a negative voltage drop. If I'm analyzing in opposition to the current, I get a positive voltage drop. In effect, I'm climbing uphill. And that's what's happened here. I'm analyzing opposite to the current, right? Here's my analysis loop. Here's my current. So this is actually going to be a positive voltage drop. You can call it a voltage gain if you want to. I'm not going to put it in the positive sign because it's implied, but I3R1 is what I'm going to get. Fair enough. If that's clear, if it's not, pause and rewind. But if it's clear, we'll keep moving. I come around through R1. I've handled R1. Now, when I get to this junction, my analysis tells me to take a turn through R2. Now I'm dealing with a different current. And notice my analysis is now going with the current direction. So I've got a voltage drop across R2. I can write down as I2, different current, R2. I2, R2 for this voltage drop. But now I'm analyzing in the same direction as the current, and my convention for that said that that will be negative. So my first two terms in this equation, the voltage drops across R1 and R2, I3 R1, I2 R2. I just pick out the current that's flowing through that particular resistor, and that gives me the voltage drop. Continue my analysis on up. The next thing I come to is the EMF E2. I've got to finish where I started, which means I need to go through the EMF over here to the positive terminal. And so I'm crossing the EMF from negative to positive. That is a climb uphill. And so I'm going to get a positive voltage drop. You might say, well, what's the voltage drop across an EMF? You might be able to convince yourself it's just the EMF. So my voltage drop, quote unquote, across E2, analyzing in this direction, going from negative terminal to positive terminal, gets me plus E2. This is a voltage, this is a voltage, this is a voltage. I'm happy with that equation. And that's all my components in this analysis loop 1. What does Kirchhoff's law say about this? That's equal to 0. And there is another equation I can use to analyze this system. I've got another loop. So, I don't pick out someplace you want to start. Let's start at the same spot on E2. Just to remind yourself what's going to happen. I'm going to flow around here through R1, come down this way now, go across E1, flow through R3, not flow through, analyze across R3, back up to E2. Fair enough? Second loop now, start here, move around. First one I come to is R1. Notice I'm moving in the exact same direction as I was for this inner loop. I'm going down. The current through R1 as I've drawn it is going up. So I'm going to get a positive voltage drop. In fact, I'm going to get the exact same term here. I3 R1 moving across this resistor in opposition to the current. Now this analysis loop does not take a hard turn here. It keeps on coming down, 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 down. As soon as I pass this junction though, I'm dealing with a different current. I remember that. Now I'm going to go across E1 and notice how I'm crossing it from positive to negative. The long line here is the positive. Positive, negative. I'm in effect jumping off a cliff here. If I cross an EMF from positive to negative, that is a negative drop in potential. So I get minus E1. The voltage drop across any EMF is just the EMF. Negative because I'm moving from positive to negative. Then I keep on going in my analysis up this way. I'm now gonna have to cross R3. I'm still dealing with the current I1. Remember, I1 here is coming down because it's gotta come up over on this side. So I1 is coming down. I'm analyzing up. The voltage drop I know is going to be I1 R3. I'm analyzing in opposition to the current, so I actually get a positive value there. And I'm not done yet. I keep on coming up, and I go across E2 from negative to positive. That is climbing uphill. We saw this a while ago. So I'm going to get a plus E2 there. And I'm back where I started. Again, it doesn't matter where you start. It matters that you finish where you started. I'm back where I started, which means that loop has to add together to get 0. And I have another equation that I can use to solve this system. So you've got to keep the sign conventions in mind. I've got two directions to consider. I've got my analysis direction and I've got the current direction. I picked both of those. I mean, sometimes you'll be given current direction, sometimes you'll be given analysis direction, but in general you can pick those as you will, as long as you're consistent. If you picked wrong, that will come out in the mathematics. You just have to be consistent. But the convention is if you analyze in opposition to the current across a resistor, that is a positive voltage drop. If you analyze with the current across a resistor, that's a negative change in potential. If you analyze through an EMF from positive to negative, that's a negative change in potential. If you analyze from negative to positive, you're going uphill, that is a positive change in potential. So I've generated 3 equations. I said a while ago, I guess I could, this is not an analysis loop, but if I'm numbering my equations, now I could write 3 there. I said a while ago that I could only get 3 out of the system. You might go, well, hold up, you have another loop, right? I have another loop in here, which involves E1, R3, and R2, I1, and I2. Could I do that? Yes, I could. I could absolutely analyze that loop and come up with another equation. The problem is that equation is going to be redundant. How do I know if I've finished? How do I know if I've gotten all of the possible loops? The answer to that is that you have every component represented in one of your equations. In this equation, I've got R1, R2, and E2. In this equation, I've got E1 and R3, and R1 also and E2. But the point is, I've covered every component between my equations. If there was a component that I had not covered, I should do another loop. To figure out when to stop doing loops takes a little bit of practice, but it's a good check. After you do your analysis loops, you're going to find that if you have covered every component, if you have a relationship between every component and some other components, then you're done. Could I have done this loop and this loop, but not the outer loop? Yes. If I had done that, this loop would handle E2, R1, and R2. This loop would handle E1, R3, and R2. So I still would have covered every possible component. But I don't then need to do the outer loop. I have 3 possible loops here. In this case, I only need to do 2 because now I've covered every component. I mean, feel free to do the other one, but it doesn't get you any new information. I've come up with a system now of 3 equations, which I can then solve for up to 3 unknowns. What those unknowns are depends on the problem. After this, it's algebra. How you solve system equations is up to you. If you like matrices, feel free to do that. I think that's probably easiest. Substitution, back substitution, things like that, that's totally fine. The rest is just algebra. It can be a little bit lengthy and a little bit tedious, but it's not difficult. The physics is done here. Now, let me talk about one more thing. I mentioned earlier that if I had guessed wrong, I would be able to tell in the future. How would that be? Okay, let's imagine that in this case, I got I1 right and I got I3 right, but I2 was wrong. Nah, let's not guess. I don't see how that would be the case. Let's imagine that I got I1 right and I2 right, but I3 was wrong. In other words, really what's actually happening is that I3 is coming down like this. Right? But I don't know that at first. I guess the red direction. What's going to happen is when I solve for I3, after I put in numbers and all that good stuff, I'm going to get a negative value. And that negative value tells me you guessed wrong on I3. Do I need to go back and rework the problem? Absolutely not. Everything is fine as long as I've been consistent. I would then just make a note, I3 is equal to 1.5 amps or whatever. And then I would make a note, or I guess what I would get was I3 is equal to negative 1.5 amps. And then I would make a note saying, the negative sign says that I picked the wrong direction. And then I would just know that I3 actually goes downward. I don't have to rework the problem. I've actually gotten all the information out of the problem I can. So it's a little bit of guesswork. It's not guessing. You're not actually guessing. You're just choosing which directions to give for your currents. Again, if you get it wrong, you're going to get an extraneous negative sign, which tells you that that particular current is actually flowing oppositely from what you've drawn. But you notate that and you move on with your life and everybody's happy.